We're going to start talking about chapter 22, section 1, and it's the scientific revolution. So it's my privilege to teach you about a time during the mid-1500s when a number of scientists began to question accepted beliefs and make these new theories based on experimentation. So first I want to go into the medieval view. So a medievalist, that is, your classical scholar from the Middle Ages, kind of pre-1500, post-500, believed that all the good things had already been discovered and thought of, and that we just have to study the Greeks and Romans, and that Aristotle was the apex of our understanding of the world, and that the Christian Bible is the dominant source for our understanding of the world. And so, as you read the Old Testament, there are a number of passages that suggest a geocentric worldview. That is, an Earth where the solar system revolves around our planet. There are a number of passages that suggest a flat Earth. Passages that say four corners of the earth. Corners. Flat. And those were the widely accepted understandings of our universe. Again, the medieval view. But as we begin to transition toward a time period known as the Enlightenment, you get a number of prominent thinkers who challenge these preconceived notions. And so, this is part of kind of tied up in the Renaissance era, from 1300 to 1600, where a lot of these thinkers are beginning to challenge preconceived notions. And so this time period that we're going to be talking about today is the scientific revolution, a major change in our way of thinking about the world. And so a few things that we'll be looking at in terms of effects of this time period: new discoveries, overseas exploration, ships traveling outside of the side of land, and also new discoveries in astronomy and mathematics. But I want to show you a silly meme here real quick. And, I wanted to challenge the notion of dismissing an argument by saying, well, we're both right. Well, that's not an accurate worldview. If you have a conflicting idea with someone else, well, it's possible that one of you is wrong. Oh my God. And the acceptance of that, well, let me just read it. It says, someone here is wrong. In the question of is it 6 or is it 9, well, someone painted that with the intention of it being a 6 or a 9. Now, to be fair, they should have put a line underneath. That's how you do it when you're not sure. But people having an uninformed opinion about something they don't understand and proclaiming their opinion as being equally valid to facts is, in my opinion, is not a good thing. People don't want to do research. They want to be right. We want to surround ourselves with like-minded people. That's called an echo chamber. The psychological term is confirmation bias. You want to surround yourself with people who agree with you because it makes you feel better. But challenging preconceived notions can be uncomfortable. And so let's start with the heliocentric theory and why this is such a big deal. So, by the time of Copernicus, the geocentric theory, that is, the theory that the Earth revolved around nothing, but that the sun revolved around the Earth, that the planets revolved around the Earth, that the sun went up and the sun went down. Well, that was challenged as inaccurate. When Copernicus developed the heliocentric theory, that planets in fact revolve around the sun based on gravitational movement, he was able to demonstrate this. In your science classes, you guys demonstrate. In physics, Mr. Honeycutt demonstrates how bodies revolve around the largest body and how gravitational pull is the explanation for this. Copernicus was right, obviously, but it challenged a long accepted view based on an understanding of a religious text. Now, when Galileo Galilei published his works and his astronomical discoveries, his discoveries supported Copernicus, and that the reason why planetary bodies move is because of gravity. And the reason why they move around the sun is because the sun is the largest object in our solar system. And so as a result, everything revolves around the sun because gravity is relative to size. Now, where the drama comes in is the church. You see, the Catholic Church attacked Galileo's work because they were afraid that since his discoveries about planetary motion and the heliocentric theory, they technically challenged passages in the Bible. They technically challenged church tradition. And so the Pope told Galileo, you have a choice. You can either say, oh, I was wrong, I made all this up, it's crazy. I didn't mean it. Or we will excommunicate you and possibly even burn you as a heretic. Galileo was he's not, out to push this issue. He just wanted to live. He wanted to continue his work. And meanwhile, Johannes Kepler was able to demonstrate and find that these orbits were in fact accurate, that Copernicus and Galileo were in fact right, and that these orbits, again, are based on gravity, and that if you begin to think about how that would work, you've got a planet, charging in one direction, and then gravity, pulls it back. And, if you begin to work out how that would look, it's the shape of an ellipsis, not a perfect circle. Now, that also challenged a number of preconceived notions, because previously, the Greek and the church tradition was that orbits were a perfect circle, because it was designed to be perfect. But it's not actually a perfect circle. It's an ellipsis. Because again, planets going in movement are going to be sucked back by gravity. And that's not going to be in this perfect little package. So here's Galileo on trial before the Inquisition in 1633. And this church governing body told him, you tell everybody you made this junk up. Only like half of us can understand anything you're talking about anyway. So just tell them you're all crazy and you're sorry. And he did. Copernicus, in fact, did not publish many of his works until he was dying. He was afraid of the church. Now, this is really just a shift in scientific thinking. Where you've got people like Rene Descartes who made that famous statement, I think, therefore I am. I think, therefore I am. What does that mean? That means when you go into a question, you have to think about it with the willingness that you might be wrong. And that if you can't go into a question with the understanding that you might be wrong, you shouldn't go into the question. If you can't have a debate with someone with the understanding that you might lose, don't have the debate. That's what Descartes was talking about. It's better not to discuss the issue than to go into it assuming that you're right. So that's the logical approach. We all get that, You're not going to debate with someone if you're not willing to listen. And in fact, Francis Bacon and Rene Descartes together came up with this method for figuring out if something is right or wrong. It's a method that you use every day. It's called the scientific method. So, yesterday, I was about to take a shower. It's the evening. The dishwasher and the clothes washer were running. So, logically, I was like, oh, dang, there's probably not much hot water. But also, I was sweaty from going for a run. So, I needed a shower. Well, logically, I knew there wasn't hot water. Okay, dang. All right. So I get to the shower and I turn it on all the way hot. Hope. Well, what do? I test the water. I stick my hand under it. I'm like, it's not that warm. I'll live. And then I say, okay, I'll take a shower. So I took a shower. Well, that was hypothesis, experiment, observation, conclusion. I utilized the scientific method and took a shower. We do it every day. We do it all the time. But formalizing it with the understanding that when you perform the experiment, when you test your theory, you have to go into it with the knowledge that you might be wrong. And, that the scientific method is all about the understanding that we can use reason to figure out basic truths. What's going to happen if I take Tylenol? Well, there have been studies done, double-blind studies to rule out the placebo effect. We know what will happen when you take Tylenol because it has been demonstrated using the scientific method. It ain't going to kill you, unless you're allergic, then it might. Meanwhile, an English scientist, Sir Isaac Newton, developed the theory of motion. Basically, he stated that the same forces rule the motion of planets, as do all matter. Now, I'm going to blow your mind for a second. If you use an electron microscope and you zoom in to an atom, the nucleus, the protons and neutrons in the center of the atom have electrons orbiting around them based on their gravitational pull. So there is gravity and there are orbits at the subatomic level. And there are gravity and there are orbits at the planetary level. I'm telling you, I remember learning that in 4th grade and running home to my dad and going, proton, neutron, electron, they have orbits, oh my God, yeah. And I was like Olivia, I just had that moment of like, oh my gosh, like you're telling me that if I zoom in, gravity works the same as if I zoom out. And that's based on Sir Isaac Newton's works and his studies on gravity and gravitational motion. So here's Isaac Newton believed that there's still room for God within this universe. That he believed that a God wound all this up like a very complex clock and then set it into motion. So, next, I'd like to get into a few scientific instruments that came out around this time period. The microscope. Now, the electron microscope doesn't come until the 20th century, but the microscope allows us to see particles that you previously could not see with the naked eye. The barometer allows us to measure pressure in the air. You can feel a change in barometric pressure, but without a barometer, you can't measure it. And then finally, a thermometer. Obviously, you can feel a difference in temperature. It was cold this morning. I think it was 30 at the house. Now it's supposed to get up to mid-50s. You'll feel the obvious difference in temperature between the beginning and the end of the day. But also medicine and the human anatomy. So, Andreas Vesalius improved on our understanding and knowledge of anatomy by beginning to dissect human corpses and to document what he found and to catalog everything he found in a human corpse. And so he was really the first to do this in a scientific manner. Edward Jenner produced the world's first vaccine for smallpox because what he observed is that smallpox is a deadly disease. We are lucky there is a vaccine for it today. I mean, it's very possible half of us would be dead by smallpox. It was one of the most common causes of death until Edward Jenner. How did he figure it out? Well, he noticed that dairy farmers weren't getting smallpox. He's like, everybody else seems to die of this. I mean, literally everybody. You know, go to a cemetery and look at the graves pre-smallpox and then post-smallpox and get the names, find the cause of death. A large chunk of them were smallpox, but not dairy farmers. Why? What is it about dairy farmers? Well, he found that there was a similar strain of smallpox called cowpox. They were getting this similar strain through exposure from milking cows. And the cowpox is not a deadly disease, but it's of the same variety, and so they were getting this disease, and they were building up an immunity to it, and then they weren't getting smallpox. So dairy farmers weren't affected by this disease that was killing millions. And they took a vaccine. So he developed a vaccine based off of that, and smallpox has been eradicated, ladies and gentlemen. Something that once killed millions, that would have killed half the people in this room by the time of your age now, doesn't kill anybody. Thanks to a vaccine. There you go. So, there's a human brain. Andreas Vesalius opened this sucker up and began to catalog all the different things in his brain and call them things and name them things using a scientific method. Next, let's talk about chemistry. Robert Boyle demonstrated and argued that matter is made up of many different particles. So, for example, he came up with a law that revealed an interaction of volume, temperature, gas, and pressure. We all understand this, that water has three basic states: gas, liquid, and solid. So the state that water is in depends on the temperature. It also depends on the volume, because we know that water under pressure has a different freezing temperature than water not under pressure. We also know water in motion has a different freezing temperature than water that's not in motion. And so there's interactions, there's relationships between the state that matter is in. For example, an atom, when heated, speeds up. An atom, when frozen, slows down. So there's an interaction in particles depending on certain forces.